All right, for the answer key for exam 2, on the first question, we're asked to name 2 of the following compounds using IUPAC nomenclature. For the first compound here, we have 1, 2, 3, 4, 5 carbons in our carbon chain. So this is going to be a pentane, and we have bromine at the 2 position and methyl at the 3 position. And we have 2 stereocenters, one at the 3 position and one at the 2 position. So I'm going to go ahead and assess these stereocenters. So we have a hydrogen as a wedge right there, and we have a hydrogen as a dash right there. So for the first one, bromine ranks first, the chain is second, the methyl is third. So this has a clockwise rotation, but 4 is in the 4th ranked hydrogen is in front. So again, we have a clockwise rotation, which would be R, but this is actually an S stereocenter. So this is going to be 2s, and then for the 3rd carbon, we have hydrogen already in the back, so that's convenient. This ethyl with the bromine on it ranks first, the ethyl with nothing on it is second, and the methyl is third. Hydrogen's already in the back. This is a clockwise rotation, so that is R. So 2s, 3r, and 2 bromo, 3 methyl pentane. For the next compound, we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. We have pentane again. We have a methyl group at the 2 position here, and we have a methyl group at the 3 position here, and we have an alkene between carbon number 1 and 2. So this is pentene, and the alkene's at the 1 position, so that doesn't need a number. I'll go ahead and draw the number into the name. And we have 2 methyl groups, so it's dimethyl, and we have 2 hydrogens on this carbon of our alkene, so this isn't an E or Z alkene. But we do have a stereocenter right here, so that stereocenter needs to be assessed. For this, for everything attached to it, we have hydrogen out here, and this is carbon number 1, that's carbon number 2, that's carbon number 3. So this is a clockwise rotation, but 4 is in front, so it's an S stereocenter. So this is 3s. And I don't need to specify the 3 since there's only one of them, but I'm just going to leave it like that anyway. 2,3 dimethyl. And then 1 pentene. And often again, you don't see the 1 in front because you can ignore it if it's 1. But it is important that this is pentene, not pentane, as I have there. All right, one more 5-membered ring. So we got one more pentene, and we have a methyl on our 5-membered ring. So this is carbon number 1, 2, 3, 4, 5 of our cyclopentene, and we have a methyl group on there. Our alkene is between carbon number 1 and 2, and we've got cyclopentene. So this is 1 methyl cyclopentene. For the next problem, for each of the following carbocations, determine if rearrangements will result in a more stable compound. Here we have already a tertiary carbocation, so rearrangement will not happen. So nothing needs to be done for this. Here, rearrangement can happen, so we can do a 1,2 hydride shift to transform this from a secondary to a tertiary carbocation intermediate. So after that arrow pushing mechanism, that gets us to cyclohexane with our methyl group there and a positive charge on that carbon. For the next question, circle the molecule that reacts fastest in SN2 reaction. So based on sterics, that carbon's tertiary, that one's secondary, that one's secondary, that one's primary. We have plenty of room for that backside attack here. So this is the molecule that would react the fastest. And then classify each as methyl, primary, secondary, or tertiary. So like I said, this is tertiary, this is secondary, this is primary, and this is secondary. All right, draw two sets of stereospecific isomers of this molecule. Each possible stereoisomer should only be drawn once. All right, so we need to draw two enantiomers of this. It looks like we have stereocenters on that carbon there and that carbon there. So the easiest one is to say that both groups are on a wedge. And both groups are on a dash. I know that specifically this stereocenter is now the opposite of that, and that one is the opposite of that. So just to double check, just for a little bit of practice, we might as well assess whether these are R or S stereocenters. For this, chlorine is ranked first. Then we've got CH2, which is tied with CH2, and then methyl, which loses to this carbon here, which has got two carbons coming off of it. So that's 2, that's 3, and hydrogen's in the back. So this is an S stereocenter. So I'll label that down there as an S stereocenter. And then for this one, we've got hydrogen also in the back, which I'm not going to draw that in, but hydrogen's in the back. What's attached to this carbon is carbon, so CH2, CH3, and CH. So this one here wins first. So that's first, that one's second, already labeled as second, and that one's third. So this is an R stereocenter. So if we were to do the same thing on here, hopefully we would agree that these stereocenters are flipped. So this one is S and that one is R. All right, that is one of my two sets of enantiomers there. And then my second set of enantiomers is, we'll go ahead and put the isopropyl group on a wedge. And my chlorine, no, chlorine is on a dash. Right there. And then the enantiomer of that is going to be chlorine being on a wedge and my isopropyl group being on a dash. Again, if you wanted to double check the stereocenters, you could. This one is going to be RR. And this one is going to be SS, just based on my assessment here. You can tell by how they look. That's what it's going to be. Another way I could have drawn this is basically draw a mirror image reflection. I thought this was a little bit easier, but if you would have done a mirror image reflection, that would have been fine too, to assess which ones are enantiomers pretty quickly. For the next, label these as enantiomers, diastereomers, or different. Explain your labels. For this one, there's a couple different ways you could do it. You could draw the mirror image. So if you were to turn this one, you could basically see if that's a mirror image reflection pretty easily, basically lining it up there. So I'm going to go ahead and redraw this turned. So again, I'm redrawing this compound here, and I am turning it so that now my carbonyl carbon is there, and when I turn it, that methyl is still on a dash and that one is on a wedge. So now I can pretty much ignore this because I've redrawn it, and I've basically have it lined up so that I have a mirror image reflection of this. But it is not a mirror image reflection. So this carbon right here does not reflect that. So in fact, if I were to flip this molecule basically 180 degrees that way, I could see that this carbon right here would directly overlap with that one. So this is in the back, that one's in the front. If I flip this 180 degrees, that would be the same as that. So this stereocenter right here is the same as that stereocenter right there. This stereocenter right here is the opposite of that stereocenter right there. So by definition, not all the stereocenters are the same, so they're not identical. Not all the stereocenters are opposite, so they're not enantiomers. They're not different compounds. They have all the same connectivity, same functional groups. They're not constitutional isomers. Again, they have the exact same connectivity. For this, these are diastereomers for all the reasons mentioned. And then for this one, another way to look at this, again, is the mirror image. That's lined up pretty well. These are not direct mirror images. So this bromine right here is not on a wedge, so this is not a mirror image of this. These are actually the same compound. So again, if you flip this 180 degrees in that way, this would directly overlay with that compound. So these are identical compounds. So we'll say for this, there is direct overlap. You can superimpose them on top of each other. And then for diastereomer, I would say not a mirror image. And one stereocenter is the same. One stereocenter is the opposite. Alright, in the following mechanism, draw curved arrows and label each step as one of the 4 arrow pushing patterns. So for the first one, it looks like we lost our O-methyl group, and electrons came from this oxygen because it has a positive charge. So drawing in the lone pairs there, we push that down to form the double bond, which we have there, and then we lose our leaving group. That gets us to here. Now we can look at how this is going to interact with our methanol. So in this case, it looks like we're deprotonating that acidic proton. Going back, that was loss of leaving group. This one's going to be proton transfer. So this is going to be our weak base, which is going to take that acidic proton to get us to our next set of intermediates. And that is it for that one. So for the next, again, draw the curved arrows for each step, and this time we don't have to label what each step is, but I'll talk about that as I go. So for the first reaction, it looks like we're forming a bond between this nitrogen and that carbon, and this oxygen has a negative charge now, and that nitrogen has a positive charge. That makes sense because we're going to use these electrons to attack that carbon and then push these electrons up to the oxygen to get us to that intermediate. To get to here, it looks like we're going to kick off a chlorine leaving group, and my electrons that are on my oxygen here are no longer there, and I formed a double bond there, which isn't there, so that's definitely where these electrons are coming from. So we'll take those down and form the double bond, and then we're kicking off a chlorine leaving group, so attached to this carbon right here is that chlorine, so that is what's going to leave. Alright, in the next step, we're doing a proton transfer reaction. We have a strong base, and we have an acidic proton there. So we will take that proton, put those electrons there to neutralize that positive charge. And for the next one, we've got, it looks like the loss of a leaving group, so chlorine is no longer there, and our nitrogen now formed a bond with this carbon. So I'm going to have my nitrogen attack that carbon and kick off my chlorine. So I did an SN2 reaction where I have a nucleophilic attack and loss of leaving group. In the next one here, we've got our intermediate, and it looks like we just did another proton transfer to convert that nitrogen from a positively charged atom to neutral. And this is our base, which makes sense because that's our conjugate acid. So it's an acid-base reaction. That takes that. And those electrons go to the nitrogen. All right, draw an arrow pushing mechanism, energy diagram, and transition state for this exergonic reaction. It looks like we have an SN2 reaction where we have a loss of leaving group, a nucleophilic attack. This is the nucleophile that attacked it. So for the mechanism, we do a backside attack, kick off our chlorine. That gives us this product. The transition state for that is, so we are attacking the carbon that has a CH2, and that CH2 has a methyl group attached to it, and we have 2 hydrogens attached to it. So I'll draw one in front and one in back, and we have our oxygen with the ethyl group and the, we'll say, partial negative charge at this point, forming a bond with that carbon, and our Cl, which now has a partial negative charge, is leaving. So this is our transition state. And for this exergonic reaction, we've got our starting materials at a certain energy level, and this is the reaction coordinate. And our starting materials are going to go through a transition state, and it's an exergonic reaction, so our products are lower in energy. So product, transition state, and starting material. All right, name at least one of the following compounds and label these as enantiomers, diastereomers, identical or different. So I'm going to redraw this as a cyclohexane ring because I think it'll be easier to see that. So for that cyclohexane ring, it looks like we have a methyl group in the up position. So on the ring, I'm going to draw that as a wedge. And we have a bromine in the up position. So again, on this ring structure here, I'm going to draw that as a wedge as well. So we have bromine right there. Now looking at this, if I flip this 180 degrees again, so if I rotate this, it looks like we have perfect overlap with that. So this is the same compound. If I were to name these, they would both have the same name, so that's one good way to double check ourselves. For the compound, I'm going to go ahead and name this one. So we got bromine at carbon number 1, and then we have carbon number 2, carbon number 3. So this is going to be 1-bromo, 2-methyl cyclohexane, but we have stereocenters there, so we need to assess what these stereocenters are. So on that carbon there, we have a hydrogen, and for our rankings, we have bromine ranked first. That carbon is second, because on the carbon one away from that, we've got 2 carbons attached, where this CH2 is equal to that one, but on this one we have only 1 carbon attached. So this is going to be third, that's fourth. If we do the rotation, that is a clockwise rotation, so it normally would be R, but 4 is coming out in front of us, so that is an S stereocenter there. And then here we have, so looking back, if I were to do it again, I probably would have done this. This would be easier to name, but you could go back and do this if you wanted and double check to make sure that that's an S stereocenter, and we'll see what this one is. All right, for this one, we have a hydrogen there for our ranking. That is going to be carbon number 1, that is 2, and the methyl is 3. So this would be a counterclockwise rotation, but that's incorrect, so this is an R. So we have 1 S, 3 R, 1 bromo, 3 methyl, and I can't fit cyclohexane over here, so I'm going to draw it down here, cyclohexane. Alright, draw the arrow pushing mechanism in the final product. So my iodide is going to come in on the front side and attack that carbon to kick off that chlorine. So now my cyclopentane ring still has that methyl group right there, and now my iodide that came in is on a wedge. Alright, that's all there is for that. And for the stereochemistry, relates to the mechanism. So we did a backside attack. So we flipped this stereocenter from what it was to what it is. So backside attack to flip one stereocenter, and that stereocenter was the carbon that we attacked. So if we're going to label this stereocenter, this is carbon 1, that's 2, that's 3, 4 is in the back. This is a counterclockwise rotation, so that is an S stereocenter. And then if you wanted to double check this, you could, but that is pretty much guaranteed to be an R stereocenter. For question 12, draw the complete mechanism and final product for the E2 reaction. So I'm going to take one of these two protons to form my more substituted alkene. We're going to take the proton, form the double bond, kick off the leaving group all in one step. And for the product, the alkene that we're going to form is the trans alkene because that is more stable. Now, based on what I've shown on the mechanism, if you were going to draw this, it would look more like the cis alkene. That is less stable. That cis alkene is higher in energy. There's more steric hindrance. There's more sterics related to the two very close methyl groups, CH3, CH3. So those two methyl groups. And then the other potential product would be deprotonating one of the hydrogens off of this carbon right here to form our less substituted alkene, which would be that. And essentially the less substituted alkenes are higher in energy. So they are less stable and less favorable products to form. All right, draw these stereospecific products and identify the major and minor products. Briefly justify your answer. So here we have a primary substrate with a good leaving group. Here we have strong nucleophile, strong base. So since it's primary, it's definitely going to favor the SN2 reaction. So we're going to kick that off. And that is the product. We also have minor E2 product with this. So we're also going to have some of that. And again, just based on the table, so here we have a primary substrate, here we have a strong base and strong nucleophile, and based on the table, that is what the resulting products would be. Here's the SN2 product, and here is the E2 product. Here we have a tertiary carbon, and here we have a large and bulky base, so this is going to be for sure only E2. And based on proton accessibility, these protons on the methyl group will be most accessible. So even though the more substituted alkene is usually favored, so usually we would take the proton on this carbon here based on sterics. One of these is going to be taken to form the alkene and kick off our leaving group. So our final product is going to look like that, where we have a less substituted alkene, but based on accessibility to the proton that needs to be taken to form the alkene, that is going to be the most dominant product. So the minor product in this case, you could probably draw two, but the other one's not really going to happen at all. Again, based on accessibility, is that product right here. And then you could also say this could be the E or Z alkene or the cis or trans. I drew the E alkene because that is more stable and more likely. Since you have free rotation, you can take free rotation on this carbon. You can take either of those to form either, and this is the more stable. So I'm going to say this is going to be the minor product. You could draw a couple more minor products, but they're so minor I would accept if you put it, but if you don't, that's fine too. For this, we have a weak base and a strong nucleophile, and we have a tertiary carbon. So based on that, this is going to be an SN1 reaction. So our leaving group is going to leave. We're going to form our carbocation. That looks like that. And then our sulfur is going to come in and do a nucleophilic attack. And then later another equivalent of that will deprotonate itself. So we will actually end up, in this case, with two products. So one of them will be where we flip the stereocenter, and then the other is where we retained the same stereocenter that we had before. So this is the same stereocenter as we had before, and this is the product with the flipped stereocenter. So that's my SH, that's my methyl, and I still have my ethyl group attached as well. And for these are both the major products.